Hello and welcome to the webcast. We're so glad that so many of you joined us today for this event, Minimize to Maximize, Minimizing Lifecycle Costs while Maximizing Power Profits. I'm Marla Barnes, the Chief Editor and Publisher of Hydro Review Magazine, and I'll be your MC today. Really glad to have so many of you joining us today. We've got a great hour lined up for you. We're very excited about the presenters and as we're all trying to do in our work, minimizing those costs and maximizing those profits. And today's conversations is all about penstocks and how to select the right materials and choose a design, the installation of a design, especially at run-of-the-river projects that will indeed minimize your life cycle costs while maximizing your profits. Before we get started today, I'd like to give you a few housekeeping tips to make sure that you have the best experience you can throughout this hour, and then I'll get right into introducing our speakers for the webcast today. At the bottom of your audience console are multiple application widgets that you can use. Now, if you have a question during the webcast, you can click on the Q&A widget and submit your question. You just type it in as we go. The presenters will try to answer those questions during this hour. If we have too many questions or don't get to yours particularly, Uponor will be providing the answers to your questions following the webcast. Now, for a PDF of the slides that you see today, you can get that if you look down along the bottom of your screen, the audience console, you'll see a resource list widget. It looks like a green folder at the bottom of your screen. That's where you can obtain the PDF of the slides that you're going to see today. Now, if you'd like to expand the slide area that you're looking at, you can do that by clicking on the Maximize icon on the top right of the slide area, or by dragging the bottom right corner to enlarge the slide area so the slides become bigger on your screen. You can expand and reposition many of the components on your screen, so feel free to play around with that as we go to really make the viewing experience the best that it can be for you. If you have any technical difficulty during the webcast, click on the Help widget, again at the bottom of your screen. It has a question mark icon, and that will address some of the more common technical issues. If you still need assistance, just type your issue right into that Q&A widget, and a member of our webcast team will work with you to correct the problem. If you've got a colleague or a client or someone that you'd like to see the webcast, we will be airing the webcast again next week on October 11, same time, noon Eastern time. So that's a chance for you to either rewatch the webcast or get a colleague to do it. And then following that, the webcast will be available on demand on the hydroworld.com website, and it will be accessible for people to watch what we call on demand. So I think that's all our housekeeping activities, announcements for the time being. I'd like to now introduce you to our two presenters for today. We have Grant Thornley and Daryl Sollenbach, both fellows who have worked in the civil infrastructure area for a long time, have great expertise, and are working now with the company Uponor. And I think they both have lots to share today. Grant, as I said, has 25 years of experience in industrial, municipal, and power markets. His real area of expertise is in pipeline infrastructure rehabilitation, asset management, stormwater wastewater management, water transmission, and condition assessment. He previously headed a consulting engineering group prior to joining Uponor Infra and worked with such companies as Pentair, GE Water, Siemens Water Technologies, NSF, and Pure Technologies. So as you can see Grant has great experience and has much to share with us today. Daryl is the regional sales manager for British Columbia and Alberta, the provinces in Canada. Daryl has an environmental engineering degree and an MBA from the University of Alberta. So not only does he understand the technical side of things, but really the business side and the profitability side of things. He's been with Uponor for 15 years, and he works in a variety of markets: wastewater, conveyance, stormwater, and now hydropower. Daryl has over 30 years of experience working with engineers and end users on all kinds of construction and design solutions. Grant and Daryl, we look forward to the presentation today. Grant, take it away.
Well, great. Well, thank you very much, Marla, to you and your team for coordinating and hosting this webcast. We're very appreciative for the efforts. Before we start, I'd like to start this presentation. I'd just like to quickly relate the reasons, or more so how this webcast came about. Daryl and myself look after the hydroelectric market in North America, specific to penstock installations and rehabilitations for Uponor. And over the years, we've been involved in probably about 150 projects to date on penstocks for hydroelectric, mainly in run-of-river. But the most common question we get from engineers is, what is the best material to use as a penstock? The answer is, of course, it depends. This presentation is intended to provide you, the end user or the engineer, with the information in which to help you make your own assessments. So we're not selling you a product, we're just offering up information for you. There we go. So some of the topics that you see here is kind of the combination of, in looking at many of the hydro assets in North America were installed, post-World War II, or almost 60 years ago. And over the course of the 60 years, the material science has advanced, as in many technologies. And today, engineers have many material choices to choose from, such as still conventional materials, such as steel and concrete, still used today, or now newer materials such as composites or high-density polymers. For run-of-river projects, we define as low-pressure, high volume. High-density polymer-based solutions, or penstock materials, are growing more in demand due to their economic benefits and structural offerings. So the intent is to kind of offer up the information between conventional and the new emerging technologies. To help you, the engineer and end user, in understanding the possible benefits when considering structural high-density polyethylene as a penstock material, Daryl and I put together, as you can see, are the following topics for your review. Hopefully at the end, the intent of this presentation, you will have a better understanding of how selecting the right material can minimize life cycle costs, and in doing so, maximize power profits. So just quickly, we thought we'd take you through. Some people don't know, who may not know who KWH or Uponor are. Just a quick overview. I thought we'd take a look at the penstock material comparisons, material characteristics of HDPE, design, engineering, fusion, installation. Take a look at kind of the cost savings associated with HDPE for consideration, and examples of past penstock installations that we've performed. So, who is Uponor Infra? We're formerly, many people know us by KWH, which we operate in North America. We've been using polymer pipes since 1951. Through an acquisition, we were renamed Uponor Infra in 2013, and by that allowed us to not only maintain our market share, but also expanded our market share in different areas. Some people know us by our systems such as Sclair Pipe, Whale Gas, and Whalite. Whalite product available since 1980, and this is what we'll be talking about today in the webcast. We're third-party certified NSF testing, CSA, UL, FM, all to ANSI and ASTM standards. We're an ISO certified manufacturing facility, and we have 2 manufacturing plants in North America. Just a very quick overview. We're about over $1 billion euros in sales. We operate in 30 countries, 14 production and fabrication sites worldwide, and employ over about 3,700 employees. So just as a basis of kind of who we are. So what do we do? Well, we are an HDPE manufacturer or polymer solution specialist, and we have three main products or solutions that we produce, which is the solid wall HDPE or sclera pipe as we define it for large pressure or high pressure applications, structural HDPE, or we call this whalite pipe for low pressure, high volume applications. And then from that, we manufacture structural HDPE panels or whalite modular, in which we can construct or fabricate things such as vault chambers, surge tanks, stormwater retention chambers, weir walls, and other components that are used within hydro applications. The combination permeation of these allows us a unique offering to our clients by producing unique or customized solutions for their needs. Just a quick overview, the penstock materials, steel riveted. A lot of this was installed back in the 1940s and more so associated with dam applications where you have more so high head pressure or higher pressures, which the tensile strength of this steel can more than accommodate. The steel riveted. Of course, steel way back then was inexpensive, not so much today, so that's part of the drivers for the development of new materials. Below that is a composite or FRP, which is fiber reinforced polymer, which is a new entrance into the market space about 15 years ago, using typically glass fiber oriented in different directions, so hoop or translateral, which provides the strength, and that material in the glass fiber is impregnated with epoxy in which to bind that together. It offers a good material for high pressures and comes in varying dimensions. Can be buried or above ground. Wood staves, an awful lot of run-of-river projects, which we'll be talking today, with a wood stave penstock applications. Reason for this is that a lot of the materials were local. They could, nearby forests, they could get their resources there, mill up the wood, and then locally install this. Wood staves, again, very inexpensive, but the downsides to it is that wood doesn't have a very long life cycle. And one of the challenges is that when wood is saturated, it will not decay or delignify. The issues are if you have to shut down the penstock and dewater, that's when the penstock starts to degrade. Wood is, again, inexpensive material, but it doesn't hold up very well to transient pressures, movement, and it does suffer from delignification from the attack from the outside. So a lot of wood staves, if you see pictures, you'll see a lot of leaks occurring from these. Concrete or PCCP pipe, which is pre-stressed concrete cylinder pipe, typically used in high pressure applications, but was also adopted for penstocks. The concrete is a combination between pre-stressed wires wrapped around a cylinder embedded in concrete, and it allows the marriage or taking advantage of the compressive strength of the concrete by keeping it in compression using those tensile wires. The problem is that sometimes those tensile wires, which are steel, corrode and snap, and then releases, you have an abrupt or a catastrophic rupture within the pipe, and we'll see that in the next slide. The last slide here, or picture I should say, is the structural HDPE or whalite as we call it. And this material was developed specifically for low pressure, high volume applications, such as that in run-of-river applications. The benefit or value of this structural HDPE pipe comes from the engineering marriage between the HDPE characteristics extruded into a specific profile. So it lends itself, the material characteristics are very robust, but the profile really lends to the structural integrity of the pipe structure, and we'll get into that a little bit more. So I just wanted to touch quickly on the type of common materials that are now out in the market space. So each material, there's a pro and cons for every material. There is no panacea in which one material will provide and address all issues. So some of the material mechanical failures that we see, or material failures I should say, for these different types of materials. Steel is mainly corrosion, which could be a result of differential soil materials. It could be galvanic, it could be low to high pH, or it could be just oxidation. So corrosion is a real issue with steel, and as such it needs to be coated or treated, or some type of impressed or sacrificial anodes to put in there to minimize corrosion and degradation of the steel. Concrete pre-stressed wires, which is the PCCP picture we saw previously. The pre-stressed wires, once the concrete is a porous material, so once water gets access to the steel, it starts to corrode them, and when the stressed wires fail, you have this catastrophic failure within the pipe. It doesn't leak, it just bursts open. And that's a real issue, particularly for above or buried applications, whereas when these pipes abruptly break, you could have extreme washout and a lot of damage in the local areas. Wood delignification, as I said, when if wood is completely saturated, it actually resists a lot of degradation. But when you have to shut it down for inspection, when the wood dries out, it causes delignification. Also because of the wet, it is a wet, and the environmental aspect to it is you'll get mold or moss growing on top of it, which then accelerates the delignification of the wood. Last is sometimes you get into FRP repairs, such as glass or carbon fiber, and what occurs if not installed properly over time, you could get delamination of the material just sloughing off the pipe, which then the pipe would then lose its structural integrity. So those are the type of material failures we see on the different types of penstock materials. Whoops. Operational failure mechanisms. Joint leaks, very common. It could be, things such as in seismic areas because the pipe is moving. It could be because of transient pressures. Someone closed a valve too quickly, which caused a spike in the pressure, which then fatigued and pushed the pipe beyond its tensile limits. So joint leaks are common. Pipe ruptures. This could be because of tensile strengths. When you have support saddles, if the saddles fail, it puts on tensile or pressures within the pipe. It could be because of just metal fatigue. Transient pressures or pulsating pressures could fatigue the metal. Different areas why, or different reasons why pipe ruptures could occur. Failed saddles or support, as I mentioned before, that if a pipe is put above ground, particularly steel or wood staves or other materials that may corrode or degradation may be accelerated by being placed in the ground, they're put onto the support saddles. If the support saddles fail, then the pipe starts to deflect and pressures and increased tensile strength is put on the material, and that could fatigue it to the point that it cracks. Failed pipe restraints. Just mentioned if you had transient pressures and the pipe is not restrained, applications such as a bell and spigot is that the bell may be forced into the spigot, expanding the pipe beyond its tensile strength, and we get cracking occurring. So those are some of the common operational failure mechanisms that we see within the field. So repair options. External repairs for PCCP pipe. We see external hoop tendons are applied using steel. with a nut and bolt and then tension down in order to put the concrete back into compression. This is typically I'm going to say a band-aid to a much larger issue, but sometimes you need to do repairs quickly. Below that is slip lining, which is simply taking an existing penstock and slipping a new line inside of that pipe. The advantage, you can use new materials. The disadvantage to something like this is that because you're putting an additional wall thickness into the pipe, you're going to be losing some of the diameters and possibly reducing the volume which you can push through, which would then translate to loss of power. Spray linings, sometimes if it's a steel pipe and you're just looking to reduce corrosion potential, or some of the linings have a better Manning's number or they're slippier. Linings such as epoxy or urethane can be applied to the surface, which to help extend the life cycle or life expectancy of the materials, as well as increasing flow velocities because of the liners are typically have less resistance. The con with liners is that they are liners and they do wear out. So if you're taking any sand or any abrasive material that's going to wear those down, you're going to lose that advantage and re-expose the steel again or other materials. Spot repairs, just quickly, it would be a coupling clamped onto a pipe. Again, it's a band-aid to possibly a much bigger issue. Internal repairs, typically using carbon or glass fiber or FRP, in which to do spot repair, surgical repair within inside large penstocks. Pro is that it's a good interim solution, but it is very costly. And lastly, what we'll be talking about is replacement. Is material nowadays designed specifically for low pressure, high volume applications can offer such economical sense that the penstock can be, the complete line can be replaced and still have a cost savings rather than trying to perform external repairs or slip lining or spot repairs. So replacement can be a much better idea than trying to do repair. So what we'll talk about today is the Whalate, which is the large diameter HDPE pipe. The large diameter really helps us in getting the differential pressure down and allowing higher volumes through. Uponor is one of the largest, or produces one of the largest structural HDPE pipe in North America. As an overview of what this pipe is, we produce diameters 18 to 132 inches. Typically in the field, we do fusion welded joints. Operating pressures in some instances can go up to about 26 psi. We have multiple stiffness classes in case it's to be buried or semi-buried. If it's buried, anywhere from 2 to 50 feet. The material, just the characteristics of HDPE, it's corrosion resistant, it's abrasion resistant, it can handle the high-low pHs if that was an issue, the salinity of water, or salinity in the soil. So it's a very robust material. The other aspect is very lightweight, and it comes in long lengths, and we'll kind of get into that a bit more. But a lot of these applications we look at are in remote sites. So having to transport a lot of materials that are very heavy can be logistically challenging, as we know. Also, that the material maintains excellent flow characteristics through the entire life cycle of the product or design life, which is about 100 years, and the lowest coefficient of friction of the materials offering for penstocks right now. So if we take a look at just getting into a little bit more detail of what Whalate is. Whalate is an extruded structural profile made from HDPE. So we're taking the characteristics of high-density polyethylene and we extrude it into a specific structural profile, in this case a closed profile, which then allows us to increase the structural integrity of the materials that we're dealing with. From this, we can produce, when we extrude this, we produce very long lengths of the structural profile. And we take that and we helically wind it onto a mandrel. And while winding it, we're fusing the sides together to produce a continuous and a pipe structure. So here we see, this is a couple of pictures from our manufacturing facilities. Again, it's a very unique manufacturing process, which we've patented years ago, and allows for the production, again, because we're winding, we can change the mandrels out to different sizes, so it allows us to go from relatively small to very, very large diameters of HDPE pipe. It also allows us, because it's continuous, we can go up to 60 feet. The length of the pipe that we transport is really dictated by the logistics of the DOT, what they will allow to be transported on the highways. But in theory, that if you wanted a 100-foot pipe and you could transport it by helicopter, we could produce that if you wanted to. It's really up to the client to dictate to us what length they want, as well as dimensions. The structural shape and association is closely controlled. That's what provides the structural integrity and provides us with a high strength to a lightweight ratio. As mentioned, the HDPE characteristics, why we have such a long life cycle or design life is that HDPE, or high-density polyethylene, is affected by acid and bases in case there's pH swings in the water, or there could be the salinity, or maybe the soil has changed. It's unaffected by corrosion. It doesn't set up corrosion cells and does not suffer from localized pitting or general wall loss, such as steel piping. And it's unaffected by bacteria, which can cause hydrogen sulfide. So it's a very robust material which allows us to offer up a 100-year design life. The other aspect of the HDPE is its abrasion characteristics. It has one of the lowest out of all the materials. And this is an important aspect to look at when designing penstocks, is that, as you know, that a lot of the pondages or the weirs, you're going to have sand or particulate material passing through. Over time, that material is going to start wearing down, thinning the pipes out. So if you have a material with very low abrasion, it allows to increase that, again, the design life on it. And HDPE, because it is I'm going to say, relatively speaking, a flexible material, it's able to absorb the energy from the impacts of those particles, and rather than having abrasion, it can bounce and release that particle again, unlike steel. Another characteristic of the HDPE is its Manning numbers, and this is probably one of the most important ones that we do discuss with engineers, because the Manning numbers is a correlation to how much friction or how much head loss can be experienced within a penstock. And as you're aware, we want to minimize the pressure differential or pressure loss within the pipe, which will allow us to maximize what our power output is. So as an example, because of the importance of this, I thought we'd just take a look at the different materials. Steel is 0.02, concrete is 0.013, our profile wall is 0.009, one of the lowest, and the whaleite is 0.01, so a very low Manning's number. The other aspect when you take a look at steel and concrete is that they start off with a very low Manning's number, but as you're aware, over time, that number begins to increase due to abrasion, corrosion, and other aspects which causes the surface to be roughed up. Whereas the whaleite pipe maintains its Manning number over the course of 100 years. So what you design today is going to be how the pipe is operating from 100 years from now. So a comparison between, just quickly, a contrast between flow comparison using pipes of the same diameter for reference. If we take a look at a 30-inch concrete pipe at about a 3.3% grade, your flow rate would be about 10,000 US GPM. For that same size pipe at whaleite, because of the Manning numbers, if we calculate it out, you see an increase of 3,000 US GPM. And that is, again, because of the lower coefficient of friction between the water and the pipe surface. So it allows us that if we're looking at a certain size, we can actually push through a higher volume of water, which again translates to more power output. if we take a look at the Manning number, but in a different comparison, but if we take the same flow rate and then take a look at example of the different pipe sizings, that if for a penstock application we required 32 USPM, that would require approximately a 48-inch concrete pipe, whereas the Whaleite, again because of the lower Manning number, allows us a 42-inch Whaleite pipe. The difference between the two, because of the installation, whether it's above or below ground, can have significant savings within the overall project costs because we're using a smaller pipe. For burial, it could be less bedding materials, a smaller trench width, and so on. So there could be material as well as labor savings in the total project offering, or savings, I should say. So the HDPE pipe, if it's buried in this application, is to show you that it is a flexible pipe. It's not a rigid pipe such as concrete. And the flexible pipe really allows us, provides multiple benefits. But when a flexible pipe or the HDPE is buried, what we're looking at is a combination of the structural integrity of the pipe in addition to the soil allowing to take some of the differential pressures that may be applied to it. So this is just an example to show that when pressure is applied, the stresses are applied to the surrounding soils. And this is important to consider, that when you take a look at the initial bedding or soil conditions, now it may change. That if a pipe in initial condition, pressures are applied to it, and it's dry, a dry soil, a dry modulus, that for a rigid pipe, when pressures are applied, it's going to will take that force full on. During wet conditions, when it's applied and you don't have that side support, the flexible pipe will bend and allow take the pressures, but the concrete pipe, because it's taking the full force and it's rigid, typically what we see is that you get crack or fracturing down the center of the pipe. The bending radii is another aspect because it is a flexible pipe in relationship to rigid pipe. By having that ability to bend the pipe to a certain radii, it allows us to eliminate a lot of fittings and couplings, which if we did, each coupling and fitting would also, because of the transition or the lips, you're going to be losing some of the differential pressure within the pipe. So by having a continuous pipe, we minimize any of the pressure losses along that line, and again try to maximize the power output to the turbines. So this is just to say that the bending radii allows us to eliminate a lot of fittings and couplings just by simply the ability to bend and curve around maybe some obstacles or making slight transitions. So by eliminating that, the bends and couplings, that also reduces our overall project costs. Creep and stress relaxation of HDPE is another important aspect of the material. You see here under creep, increasing strain under constant load, is that yes, the material will creep and will extend. So it is reacting to stresses or strains being applied to it. The stress relaxation is that as decreasing load under fixed strain. What this is on the right-hand side, what this is to present is that if we see a pressure, a stress that we're applying to the pipe, this is 12,000 pounds, that over time that the stresses, the internal stresses within the material will reduce. So it will compensate for that. And this is an important aspect if we do bury the material, and let's say some of the bedding or something is trying to push into the pipe, it will respond and the pipe will relax. If we have a material such as a rigid pipe that does not relax, and you have the constant stresses, the constant stress can result in a rupture of the pipe. So this creep and stress relaxation is to highlight that the material can adopt adapt to its environment and reduce the stresses over time that's being applied to it. That's a unique characteristics of the HDPE. When we get into the design, so that's the material characteristics and the design and engineering of the pipe, when we are taking a look at applications, of course the first question we ask is it above ground or below? Is it a semi-burial or burial? Regardless, what we will do is be taking a look at deflection, buckling, and crush. The common design practices is about 7.5% deflection. We're very conservative in our design. We'll use about a 5% deflection. If not, if it's above that, then we'll go to a higher ring stiffness. Buckling, taking a look at the soil stiffness into consideration. Stiffness is more important than the soil stiffness when buckling is primary. And this is why when we take a look at the buckling side, why Uponor, or the Waylite, is manufactured or produced with several ring stiffnesses in which to address different buckling requirements. And lastly, crush is the pipe wall is designed with sufficient thickness. Again, we have varying ring stiffnesses or different pipe profiles in which we could take a look at in which to address crush design requirements. Overall, there are other aspects in which we consider doing our design and engineering, but rather than get into each one of those areas, Uponor offers on our website, uponor.com, we have an online design calculator which I'll offer to any of the end users or engineers to take a look, visit the site, and you can online take a look at design parameters and design up your own applications. Any questions on that, please feel free to give myself or Daryl a shout, and we can kind of walk you through the online calculator. So thermoplastic welding and fabrication. I'll now transition this over to you, Daryl, if you can.
You betcha.
Okay.
Thank you, Grant. Thank you, Grant, and good afternoon to everybody attending. We'll now enter the thermoplastic welding and fabrication section and talk about installation and as well as a few projects that we've done in the past. The two methods of, well, it's one method of welding the pipe is through air fusion and extrusion welding. They basically both accomplish the same thing. Typically applies a filler material to the joint to form a pool of molten material. The weld pool, that is called, that forms to form a joint that is typically stronger than the base material. Actually, not typically. We state that the joint in the field is stronger than the pipe itself. And the reason being is you get more penetration through the joint than you do through the actual profile wall. The idea is to heat all three materials to fuse to create a homogeneous section, the filler, the base A, and the base B materials. And what I tell people is that you imagine two ice cubes side by side, you add some heat to it, you melt it, it all forms as one big lump, and then refreeze it, and you've got a homogeneous section once again. So that's basically what we're doing with extrusion welding on our Waylite pipe. Temperature ranges anywhere from 480 degrees Fahrenheit all the way up to 1,022 Fahrenheit, depending on the material thickness and the type. Here's some pictures or sketches of what these fusion welds look like. The hand fusion weld with the air behind it at roughly 1,000 degrees Fahrenheit, and then our extrusion welding to the right. And this is typically, the extrusion welding is typically what we do in our factory, and it's typically what we do in the field. We don't do a lot of hand fusion welding, but both accomplish the same thing. One, the extrusion welding has a larger bead right from the get-go, and the hand fusion weld is more of a buildup of ribbons of polyethylene to create the weld. And you can see in the sketch here just how the extrusion welding works. We feed in through either granulated product or wire into the extruder, which is basically turning all the time. And as it's turning through, we heat that up to 465 degrees Fahrenheit, and then we begin extruding that between the two materials being joined together. And on the left-hand side, you see that picture. That's our internal welder, which is typically used on power projects. It's developed by Uponor Engineering in Finland. There's 3 of them worldwide. 2 of them exist in North America. And that's a full profile semi-automatic weld, so it's basically starts welding right from the inside of the pipe right through to the outside. It's a very strong pressure rated joint and stronger than the pipe itself. The science of welding, and it is a science, there's standards that we belong to and have to adhere to through the American Welding Society. And there's standard welding procedures, specifications for welding procedures, and performance qualifications for thermoplastics. We have to have it approved American national standards through the Institute. And within that standard, it specifies the qualifications of the personnel and the procedures that they have to use, as well as the qualifications specifies welding position and the equipment that has to be used in order to properly extrusion weld this material together. We also adhere to the European Society through the German Welding Society. The installation is also to a science. It's to the ASTM D2321 standards. It has specific dimensions that the bedding has to be, as well as the trench width has to be of a specific dimension, and the burial above the pipe also has to be a specific dimension. The materials being backfilled over top of the pipe and being used as the bedding is also very specific. We look for materials that are class 1 or class 2 at 90% compaction should give us a soil modulus of about 2,000 psi. And again, that's the science that we adhere to for the installation of the Whalite pipe. You can see in this picture here that the pipe can be semi-buried. We prefer it to be completely buried, but in instances where the ground is very rocky and there would have to be a lot of blasting undertaken, which is very expensive, then it's perfectly okay to semi-bury the pipe up to the spring line. This pipe is fully UV protected, so exposure to sunlight is not a problem whatsoever. We use a lot of this material for mine tailings, and those pipelines are typically on the ground 24/7, so there's actually no effect from UV degradation whatsoever. Installation, long pipe lengths and long Whalite comes in very long lengths of pipe, which provides the benefits of course, that's going to minimize the number of joints through longer lengths. It's going to speed up the installation, and that minimizes shipping costs. And obviously, smaller equipment is required to lift this pipe into place because it is so light. About 1/10 of that of concrete, and so we don't need cranes on the site, which is very good because when you're on a hydroelectric power project on the side of a hill, you don't want to be lifting heavy pipe. And in some instances, we've been able to get up to over 1,000 feet of pipe installed per day. The other thing we can do with this pipe is that if you have a project that is utilizing, say, a 96-inch diameter Whalite pipe and a 78-inch diameter Whalite pipe, we can nest this pipe together and ship that way, and so our shipping costs are pretty much reduced into half. We can transition to different materials, and the reason why you want to do that in power projects especially is because we'll pressure out at roughly 22.5 psi, and but that doesn't stop us from being involved in penstocks because we can flange up the steel after that. And the advantage of using a Whalite in this fashion is that it's cost effective, It's maintenance, pretty much maintenance free. It's light, easy to handle. You don't have to worry about any types of coatings. And so contractors love it, owners love it because of those benefits that it has. And then when we pressure out, then you can move on to steel after that. In that lower picture there, that's our typical way that we would install Waylite into concrete structures. So no problem tying into concrete intakes or any kind of sort of concrete structure that is involved within your power project. We can make all kinds of fittings and reducers. Most of the power projects that we are involved with have a great deal of fittings that we have to undertake and fabricate. So those would be elbows. We have manholes with blind flangers because these manholes are under pressure. We've got a lot of times we'll go from 120 inch down to 108, down to 102. So we'll manufacture reducers in order to do that. We can manufacture all kinds of fittings in order to install, for example, pressure release valves. So whatever instrumentation you have on a particular power project and you got to get it mounted to the pipe, we can certainly do that. There are definitely some cost savings associated with the installation. Minimum fittings are used for the installation. Pipe can be semi-buried up to the spring line without the need for saddles or concrete supports. The long lengths of pipe allow for fewer joints. Lightweight allows for smaller and less expensive moving equipment. No cranes are required. Longer lengths and lightweight reduces the freight costs. And I mentioned earlier about the possibility of nesting different sized pipes. And the flexibility of the pipe reduces restraint blocks. And it's less expensive than steel and other materials, especially when you look at the maintenance cost of one versus the other. You have also cost savings in operation. High-density polyethylene maintains its low manning quotient, manning number throughout its design life. I've done several walkthroughs of Waylite pipe that has been installed for 5 to 7 years, and there's no buildup on this pipe whatsoever. It's so slippery that nothing really has the chance to lend itself to the surface of the pipe. When polyethylene is used, a reduction in hand loss can be realized when compared to steel, concrete, or wooden staves. An increase in pressure anywhere between 10 and 20 psi can be realized in some projects, which correlates to higher turbine outputs and in higher revenue, obviously, with higher power generation. There are major cost savings in maintenance as well. It has a 100-year design life due to the robustness of the material. There are no liners or coatings to be maintained. And I mentioned earlier, I've done several walkthroughs, and our pipe is just in almost the same condition as it was when we first installed it. It doesn't require impressed or sacrificial anodes as it is corrosion resistant already. As you would see with steel pipe, obviously it has to have those anodes attached to it, and it can withstand seismic and to a degree thrust movement without any major thrust blocking or anything like that to keep the pipe in place. I'll now turn to some installations that we've got in place. This is Pacific Core hydroelectric water supply in Big Fork, Montana. This is actually the first one we did in 2000. And Black and Beach were the designers. There's a typo error there. The actual operating pressure is up to 8 psi. Tight, reliable joints, excellent flow characteristics, long lengths reduce the installation time, and very corrosion resistant. It actually replaced a wooden stave on this project. You'll see from this picture here, water supply to the turbines was divided between a concrete-lined open channel and a buried wooden stave pipe. In this photo, the old wooden stave line was to the left of the concrete channel. The same alignment was selected for the replacement of the Waylite pipe. And here's just a picture of the pipe going into place. It's quite a deep installation. There's probably 3 or 4 meters of cover on top of this pipe. And again, running at 8 psi low pressure and 120 20-inch RC250 pipe was used in this particular case. I believe the power generation was able to increase by about 10% just by going with this smoother type of pipe. The second project we did was back in 2003. It was owned at Rutherford Creek, which is just north of Whistler towards Pemberton. It was originally owned by Cloudworks, and a few years later, Intergex took over the project, running at 8 psi, 120-inch RC250, reducing down to 108, and it's running for about 3 kilometers, and then at that time, it switched over to steel, which ran into the turbines. You can see that it's semi-buried, but that's only during the construction. This pipe will be fully buried, or is fully buried, after the construction was complete. You can see the side of the hill that it's being installed onto. So the contractor is very pleased with the lightness of the pipe and the minimal type of equipment that they had to use to install it. The next one we did was in 2006. This is the Fire Creek project, the owner being Intergex. 84-inch diameter, running at 17 psi before transitioning into steel. Again, this would be a fully buried pipe. What you're looking at is just up to the spring line for now, but that pipe will be completely backfilled once construction was completed. This is the Douglas Creek project. The Fire Creek and Douglas Creek and the Tapella, I'll show later, were all done just north of Harrison Lake, which is Harrison Lake is about 3 hours east of Vancouver, BC. The Douglas Creek one was running at 13 psi, again built back in 2006. The designers, Knight and Piso. The contractors were Peter Kiewit on all these projects. It's quite snaky and windy, as you can see there. A lot of elbows involved in this particular project, but it's generating about 25 megawatts as we speak. And the third one in this tripod, I'll call it, near Harrison Lake, was this 66-inch project called Tapella. And again, Knight and Piso, Peter Kiewit, the contractors, running at around 12 psi and going for about 1.5 kilometers. And a more recent one, completed in 2009. This is owned by Alterra, 120-inch RC250, running at 15 psi. East Toba is located about an hour's boat ride north of Powell River. You can see that flange connection at the very end, which is tying into the steel. They invited us to do a walkthrough, myself and Jerry Groen from engineering. Had to do a walkthrough with these folks in 2014, and the look of the pipe was just amazingly in great condition. We had no issues or anything to concern ourselves with. The deflection of the pipe was all to where it had to be, and they're generating the power that they were supposed to be producing, and that's very happy with the inspection. And the cost of doing that inspection was just our time to walk through, so very minimal maintenance cost on any of these projects.
Well, great, Daryl and Grant. That was fantastic. Some really good information, lots of good practical applications, and actually we've been flooded with questions. Grant, one in particular that we're getting several of the webcast participants asking, is the HDPE pipe suitable for above ground installations? And then if so, could you talk about the feasibility of the estimated maximum diameter and unsupported length that would be feasible?
Thanks, Marla. Yes, so the pipe can be installed above ground, which is beneficial, particularly if you have rough terrain, remote locations that you're going to have difficulties trenching. The only requirement we say that if you're going to do above ground is that the pipe should be buried up to the spring line in order to help maintain its strength and the roundness within the pipe. The other aspect, so I think someone had asked the question on the pipe roundness, that how do we maintain it during shipment? We take all precautions to ensure that it does maintain, it doesn't become oval, but by not stacking the pipe and so on. So there's logistics and the size of the pipe and how we're going to transport it onto site. If it does get to site, and there could be pending circumstances why it becomes oval, when we fusion weld the pipes together, what we do is we put a clamping collar onto the external of the pipe, which then brings it back into its roundness. From there, then we do an internal weld and possibly an external weld. So what we do to answer the question is that if it is out of roundness and oval, by putting the external clamp onto it prior to welding, it brings it back into roundness.
Okay, very good. And Daryl, another question that seems to be popular today from the webcast attendees is, can these large diameter pipes be field fabricated?
In order to do that, you'd have to have a whole manufacturing facility, but you can, which we don't have, but you can make field adjustments in the field with the tools that we bring to the site. So, if you have an elbow or something that's out of alignment, you can correct that in the field. If you want to locate a manhole in a different location for whatever reason, you can certainly do that. You can patch up the area where it was going to go and move it to another area. You can definitely install lateral connections in the field. Pretty much any type of corrective action that you need to bring the pipe into alignment or roundness, we can do in the field.
Okay, very good. And then I know many of you ask lots of questions about surge pressure and PSI related questions, and we're not going to have time to answer all of those today, but Grant and Daryl will look through all your questions and get specific answers to each of you on that. But one in particular, Daryl, I thought that might be interesting to answer quickly here before our hour is up. Is there an allowance for surge pressures above 26 PSI?
Yes. So typical of the HDPE, if you're surging on an occasional basis, you can go twice the working pressure. So if the project is designed for 15 PSI, you can surge that to 30. If it's designed for 22.5 PSI, you can just surge that to 50 or 45, I should say. And then if it's frequent, forever, if you have very frequent surges due to frequent power outages, you can go 1.5 times the working pressure. So if you're running at 15 PSI, you can surge that to 22.5 PSI on a frequent basis.
Okay, great. That's very good. Here on the screen, we are seeing contact information for both Grant and Daryl. Guys, give us some direction, guidance, if our participants would like more information beyond what's in that PDF the PDF file that they can access through the resource list button, that green folder at the bottom of your screen. So they need more information. They'd like maybe a pricing proposal. How would you suggest they reach out to you all? What's the best protocol there?
Probably through me, Daryl. Just send it all to me. I have a certain geographic area that I look after, but if it's outside that, I'll make sure it goes to Grant, and he'll make sure it gets to the right person.
Okay, perfect. So as you all can see there on the screen, Daryl's email address is right there. He is in Canada, but can get you information no matter really where you are in the world. So be sure to reach out to Daryl with those questions that you had. And as I said, you can look for answers that will be coming from Grant and Daryl to your questions today. on behalf of Uponor and Hydro Review and Penwell, I'd like to thank you, Grant and Daryl, for being part of this, and of course thanking the audience, the participants today. A quick reminder, this webcast will be re-airing, will be playing again on next Tuesday, October 11 at noon Eastern Time. So if you'd like to watch it again or like to get colleagues to watch it, please plan to join us on October 11. You can register for that just like you did for this one on the Hydro World website. And then after the webcast next week, the webcast will be archived. It'll be available through Hydro World, so you can watch it in an on-demand kind of setting, and also be a reference for you in the coming months. You will get a reminder email message with information about how to access that on-demand archived portion of the webcast. Once again, we thank you for taking time out of your day today to join us, and we hope this has been helpful for you. Have a great day.
Thank you.
Thank you.